Let's jump right into a massive engineering puzzle today. How exactly do you power an offshore platform when you're starting with a completely blank slate? Seriously, imagine you're handed a blank sheet of paper and told, go design the electrical system for this brand new facility. You literally can't size a single cable, you can't pick a generator, and you definitely can't specify a transformer until you nail down one fundamental number. How much electrical load does this plant actually need?
And the stakes here are astronomically high. That number, it isn't just handed to you on a silver platter. It has to be rigorously, meticulously calculated. Because think about it, if your load estimate is off, you either build a grid that trips and blacks out on day one, completely stalling production, or you end up wasting millions of dollars on massively oversized equipment. Neither of those is exactly a great day at the office.
So, to demystify this whole process, here's our roadmap for this explainer. 1. Sizing the power grid. 2. Categorizing electrical loads. 3. Core load schedule calculation. 4. Running and peak loads. And finally, 5. The N1 sizing philosophy. Let's get into it.
All right, section 1. Sizing the power grid, from macro to micro.
Load estimation is absolutely the very first step in electrical systems design. Why? Because it brings much-needed order to a totally chaotic web of thousands of components. Honestly, it helps to think of an industrial grid kind of like building a house. Before you go and select the size of your main water pipes, you have to know that not every single tap, shower, and toilet is going to be running at the exact same time, right? Well, on an oil and gas platform, it's the exact same principle. We need a realistic total demand, not just some blind brute force sum of every equipment rating plate on the rig. Moving on to section 2, categorizing electrical loads, bringing order to chaos.
So out on a platform, we start taming these massive amounts of equipment data by categorizing every single electrical load across 2 critical dimensions. The first one is criticality. Basically, if power drops, does it jeopardize human safety? If yes, those are vital loads. Think fire and gas detection systems, which are strictly fed by a UPS. Now, if losing power just causes product degradation, we call those essential loads, like your main process pumps. And if losing power has absolutely zero effect on safety or production, like, say, the lights in the galley, well, those are non-essential loads.
Now, the second critical dimension is the duty category. Within those criticality levels we just talked about, we have to classify each load by how often it's actually running. Is it continuous, meaning it's humming along 24/7? Is it intermittent, maybe running less than 30 minutes an hour? Or is it standby, literally just sitting there gathering dust, waiting for another system to fail? Which brings us to our main focus today, section 3, core load schedule calculation, the spreadsheet masterclass.
All right, this is where the magic happens. Let's look at how all this data builds into the ultimate document for engineers, the electrical load schedule. Basically, for every single load on the platform, you record its rated power, its power factor, and its duty category. But wait, you don't just add those raw numbers up. That would be a disaster. Instead, you apply a very crucial mathematical multiplier known as the diversity factor.
So picture the engineer building this out in a spreadsheet, row by row. You take that raw equipment rating, assign the category, and then multiply it by the diversity factor. That gives you the true, realistic kilowatt contribution. For instance, our main oil pump is a continuous load, so it contributes a full 100% of its rating. But look at that HVAC fan. It's intermittent, so we only count half of its load. See how that works?
So the real secret sauce here are these diversity factor rule of thumb heuristics. This is totally the industry standard for new designs. Continuous loads get a factor of 1.0 to 1.1, sometimes a bit over 100%, just to account for system losses. Intermittent loads get a 0.5 to 0.6 factor. And those standby loads, they get a tiny 0.0 to 0.1 factor because, well, under normal operation, they are effectively turned off.
Okay, section 4, running and peak loads, synthesizing the math.
Once that massive spreadsheet is fully populated, we synthesize all those diverse rows into 2 absolute powerhouse equations. Let's start with the first big one, the total plant running load, or TPRL for short. This calculates the actual active power consumed during normal day-to-day platform operation.
It is so cool to watch how this formula logically pieces together. TPRL equals the diversity factor of continuous loads, which is our D, multiplied by the sum of continuous loads. Then you add the diversity factor of intermittent loads, DI, multiplied by the sum of intermittent loads. But notice what is completely missing here. Standby loads. Yep, because under normal, steady-state running conditions, standby loads are entirely de-energized. But as you guys know, we can't just rely on the everyday running load. To ensure absolute safety and grid stability during those worst case, everything goes wrong operational scenarios, we have to transition our calculation. We need to find the total plant peak load.
And doing this is actually pretty elegant. We just slide a brand new term right into our previous equation. For the total plant peak load, or TPPL, we just append the standby load calculation to the end. That's ds times S sum. Adding that ensures we've captured the absolute maximum capacity needed for those rare, chaotic moments when backup systems kick in, but the primary systems might still be drawing power. Just to prove this math actually works in practice, the source material gives us a brilliant real-world example. A single low-voltage process switchboard on an offshore platform, once you apply all those continuous, intermittent, and standby diversity factors we just talked about, synthesizes all the way down to a highly precise normal running load of exactly 1,920 kilowatts.
Finally, Section 5, the N1 sizing philosophy, engineering for reality.
So, the big question, how do we take this meticulously calculated peak load number out to the real world to actually order our massive multi-million-dollar generators? Well, we use what the industry calls the N1 philosophy. We don't just buy enough generators to perfectly match the peak load. No way! We buy N generators. Basically, we install enough capacity so that under normal operations, we're using N-1 generators, running at a super efficient 70 to 85% load factor. That way, if one unit suddenly trips offline, the remaining running units can absorb that massive peak load spike without exceeding a 125% overload limit. It keeps the platform up and running without missing a beat. As you can see, offshore platforms inevitably expand over their 30-year lifespans. They're always adding new pumps, bigger processing modules. So balancing that precise, rigorous spreadsheet math we just walked through with the pure art of future contingency, that is what truly makes a master electrical engineer. Which leaves us with a pretty big question to ponder. In a world of ever-changing, unpredictable operational demands, how much contingency is truly enough? It's a puzzle engineers literally solve every single day. Thanks for hanging out with me for this explainer, and I'll catch you on the next one.